Here is an example of an integral we can solve using partial fractions. I have the integral with respect to y of 3y plus 39 divided by the quantity y plus 4 squared times 2y minus 1. The first thing I am going to do is break down the partial fraction decomposition of our integrand, which is 3y plus 39 divided by y plus 4 squared times 2y minus 1. Notice that the bottom of this fraction is already factored for us. If it were not factored, that would be our first step. When I break this down, I notice that I have the factor y plus 4. So I have a fraction that has y plus 4 on the bottom. Because the y plus 4 is squared, I have a second fraction that has y plus 4 quantity squared on the bottom. Lastly, I'll have a fraction that has 2y minus 1 on the bottom. Now, because y plus 4 and 2y minus 1 are both linear factors, each of these fractions just has a constant on top. We're going to call those a, b, and c. Notice that it actually doesn't matter what order you write these in. Now I'm going to clear the denominators by multiplying this entire equation by y plus 4 squared times 2y minus 1. This gives me 3y plus 39 equals a times y plus 4 times 2y minus 1 plus b times 2y minus 1 plus c times y plus 4 squared. And now I'm going to multiply everything out on the right side. Now we are going to do what is called equating coefficients. And the idea here is that if I focus on the variable y, I have a polynomial on each side of this equation, and two polynomials can only be equal to one another if their coefficient on each power of the variable y are equal. So on the left side, we can imagine 0y squared in front here. So if I need the coefficients on y squared on the left side and on the right side of this equation, then the 0 from the left side must equal the 2a plus the c from the right side. Similarly, we're going to look at the coefficient on y. On the left, I have 3y, so the coefficient is 3. On the right, my terms that have a y are 7ay, 2by, and 8cy. So the coefficient on y is 7a plus 2b plus 8c. And lastly, we're going to look at the constant term. On the left, my constant term is 39. On the right, my constant term is negative 4a minus b plus 16c. We have three equations in three variables, so we are going to solve this system of linear equations. Here is our system of equations. I'm going to take the top equation and solve for c in terms of a. So c equals negative 2a. Then I'm going to substitute negative 2a in for c in each of these equations. So my second equation becomes 3 equals 7a plus 2b plus 8 times negative 2a. Or in other words, 3 equals negative 9a plus 2b. Similarly, my third equation becomes 39 equals negative 4a minus b plus 16 times negative 2a. Or in other words, 39 equals negative 36a minus b. Now I'm going to eliminate b from these two equations. So this equation is 3 equals negative 9a plus 2b. I'm going to take this equation and multiply both sides by 2. So we get 78 equals negative 72a minus 2b. Now, if I add these equations together, the b's will cancel. So we have 81 equals negative 81a and no b's. Now I can solve for a. We get negative 1 for a. Then I can substitute negative 1 in for a here. We get 39 equals negative 36 times negative 1 minus b, which gives us 3 equals negative b, or b equals negative 3. And remember I had c equals negative 2a. I can substitute negative 1 in for a here and get c equals 2. So a is negative 1, b is negative 3, and c is 2. Now, let's go back to our initial partial fraction decomposition. Here is our original decomposition. We just solved, we figured out that a is negative 1, we figured out that b is negative 3, and we figured out that c is 2. By rewriting the integrand as the sum of these three fractions, we can rewrite the integral as the sum of three integrals. So our original integral is equal to the integral of negative 1 over y plus 4 dy plus the integral of negative 3 over y plus 4 squared dy plus the integral of 2 over 2y minus 1 dy. In each of these integrals, we can, of course, pull the constant out front. So we have negative 1 over y plus 4 dy minus 3 times the integral of y plus 4 to the negative 2 dy plus 2 times the integral of 1 over 2y minus 1 dy. Now we are ready to integrate. The first integral, 1 over y plus 4, we recognize as the natural log of the absolute value of y plus 4. The second integral I rewrote like this so that we can just use the power rule. We have negative 1 times y plus 4 to the negative 1. And our last integral we recognize as the natural log of the absolute value of 2y minus 1 times 1/2. This 1/2 may be more obvious to you if you use a substitution u equals 2y minus 1. Because this is an indefinite integral, I'm going to add plus c, and we can clean it up by writing negative natural log absolute value of y plus 4 plus 3 divided by y plus 4 plus natural log of the absolute value of 2y minus 1 plus c. This answer is completely acceptable. I do want to remind you about this rule of logs, that if I have one natural log minus a second natural log, we can combine them into a single natural log by dividing. So that we have the natural log of 2y minus 1 divided by y plus 4 plus 3 over y plus 4 plus c. Either of these last two lines would be an acceptable answer in my book, but I did want to remind you about this natural log rule.